after Ian's very generous remarks at the beginning of this workshop. But I would have felt very guilty if I hadn't said something of thanks to a lot of people for the workshop and the program. I'll first thank very much Ian and Peter for everything they've done to, I hope, make the whole thing a success. And then, again, I hope, with the permission on their behalf, I'd like to thank a whole lot of other people, all the organisers of workshops, organisers of, this includes the very successful one that David Barber ran last week, organisers of satellite workshop in Warwick, see how much we enjoyed linking up with the statistical laboratory from time to time. We enjoyed going and eating their cake and having them visit us from time to time. And we had visits from the Microsoft, the machine learning, Microsoft comes later, machine learning group in the engineering department with Zubin. That was a very nice contact to make. It was very nice to have so many wonderful visitors here at the workshops and throughout the program. Perhaps I should mention especially David Donahoe, who is our Rothschild visiting professor. And mustn't forget the Institute staff who really makes the scientific organizer's life really very simple in terms of all the organization. If any complicated issue crops up that people mention to us, we just send them to the reception desk, and I think it all gets sorted out. I should also certainly mention Microsoft through Chris Bishop. They very generously made a financial contribution that went a long way towards supporting people, especially coming to the workshops. If you got special funding to come to the workshop, then probably was by courtesy of Microsoft. I thank all the other people that I've forgotten, but I'd like just to give special mention to someone who's not here, and that's David Banks, who with Ian, Peter and myself was on the panel of organisers, and I think there's been a good spirit throughout the program in terms of groups going to lunch and little extra events. And he was definitely very much an initiator of that sort of pattern. So he certainly should not be forgotten. But thank you to all these people.
I think we can't close this workshop without doing it to Mike again. And I think everybody's appreciated this workshop, which I think will end on a high, and this whole program, which would not have happened without Mike. And I hope you've all enjoyed it as much as I have, and I think I can speak for Ian as well. And so I'd like to thank Mike again. Okay, so last but certainly not least, my colleague John Rice will talk about some real science, the Taiwanese-American.
Well, thank you, Peter. I feel a little bit like an after-dinner speaker at a dinner which has had many, many excellent courses and separate wine with each course. At this point, you probably only have room for some brandy and maybe my role is to tell funny stories. Well, I hope you will find some amusement in some of the data I'm going to show you at least. So the outline of that talk, I'm going to talk very, very quickly about the astronomy background and the role of this survey called the Taiwanese-American Occultation Survey. I'll spend a little bit of time in looking at how measurements are made because it affects the data. and then I'll look at some examples of some of the data that come off of this, and probably spend a fair amount of time just looking at examples. I'm not going to explicitly highlight. I'm not going to try to formulate statistical methodology explicitly as we go along. I'll say a little bit, but I think that some of the ideas are suggestive and maybe kind of implicit in some of the things I'm going to say. So there's an object called the Kuiper Belt in the solar system, was postulated by Kuiper in 1951 and was first directly observed in 1992. This is a region roughly out beyond the orbit of Neptune, which is believed to be the remnants of the early formation of the solar system. And it contains a large number, nobody knows how many, of objects of various sizes, and nobody knows how many, what the size distribution either, although there are some theories that the size distribution should scale like a power law. So people are interested in this for a variety of different reasons. One is because a better knowledge of the Kuiper Belt would tell a lot about the evolution of the solar system, and also because the Kuiper Belt is one of the origins of planets that pass by the Earth. There are two belts, the Kuiper Belt, in which things have been observed, which is a few hundred astronomical units, that is distances from the Earth from the Sun. Out beyond that is an area called the Oort cloud, in which nothing's ever been directly observed. The short period comets tend to come from the Kuiper Belt. They're kicked out of the Kuiper Belt by some gravitational forces, whereas the longer period comets tend to come from the Oort cloud. These comets can impact the Earth, as the picture from Arizona shows, and so sometimes in searching for funding for this project, we call it Search for the Death Comet. The big Kuiper Belt objects have been directly observed by telescopes. People focus on a rather narrow beam looking in a particular direction, and they look and they look and they look night after night, and they see if something moves. And then from how much it moves, they're able to deduce how far away it is. The most spectacular of these objects is something called Sedna, which is maybe around 1,000 miles in diameter. It has a very eccentric orbit. Now we're interested in very small objects, that is, objects which could not be observed by telescopes on the Earth, at least, because the amount of light they would reflect back to the Earth is too small because of their size in order to be seen directly. So the technique which this survey is exploiting is something that's called occultations in astronomy. And the idea is kind of simple, that if you look at the light from a star here, and one of these comets or Kuiper Belt objects passes between you and the star, you should see that light dip a little bit, depending on exactly how much of the surface of the star is occulted. As we'll see, this happens in a time scale of about 0.2 seconds or so. So it's pretty fast. We're employing 3 telescopes, and we're looking for sort of more or less basically simultaneous events on all 3 telescopes. The Taiwanese-American occultation survey is joint between astronomers in Taiwan, some in the US, a group in South Korea. At Berkeley, I've had the good fortune to work with Qinglan Liang, who is a graduate student, who worked on this problem, I don't know, must have been like 8-10 years ago. And we're thinking, maybe, Qing, you should stick around till we get some actual data to analyze. She was doing a lot of planning. How would you do this statistic? She's running a lot of simulators. If she had stayed around to get data, she would have just gotten her PhD maybe this year. So, but she actually made a lot of contributions in thinking about what one should do and thinking very clearly about different scenarios. I was also fortunate to have that Nikolai Munchausen was a postdoc at Berkeley and worked with me on this project, and a current graduate student, Nate Coelho. The project will use 4 robotic half-meter telescopes. Right now there are only 3 for technical. 4 exist, but 3 work. The reason the 4 don't work is there's just not enough time to get the 4th one working. There have been all sorts of engineering problems and practical problems, And yet this is located in the interior mountains of Taiwan at Yushan National Park, which is about 2,000 meters in height. And it's sort of surprising, the interior of Taiwan is sort of remarkably alpine. So you might think it's not a bad place for astronomy. It's not a bad place, but it's sure not a good place either. There's a lot of humidity there, and we'll see some of the effects of that later on in the data. I want you to notice that the telescopes we're using are labeled A, B, and D. And it's just important to remember for what we see later that A and B are not that far apart, and that D is further away than either from the other two. There's a picture of one of the half-meter telescopes. So the data are recorded on 2,000 by 2,000 CCD arrays in a way that's quite interesting and that I'll describe. So here's the ideal. Here's the ideal thing. Nothing's going on. You just measure the light from the star. It should be constant. There may be variable stars, but you can screen that out. Many of them are known already. You can test whether the star is periodically variable. So imagine we're just observing stars whose under ideal conditions, the light should just be constant. Okay, and then you're looking for interruptions on this. There's inevitably noise. You never get down below the level of noise which is inherent to the photon counting statistics, plus certain sources of noise within the CCD array. You can see that noise in these three traces, but the noise you see here is well above the Poisson limit. So there's a lot else going on here other than just Poisson noise. The idea is that to observe a field of stars, so a field to be selected, and in each star, in each field, you'll monitor the light from a few hundred to 1,000 stars. And this will be monitored, say, maybe for about 90 minutes at about 5 hertz. And then maybe another field will be selected. So that's how the data is coming in. You can imagine we've got 90 minutes of data from 1,000 stars. We've got about 28,000 observations on each of, say, 500 to 1,000 stars during 90 minutes. This should ideally run every single night of the year. But in fact, it doesn't. The telescopes break. It's cloudy. There's a monsoon season, and et cetera. So we don't get nearly that amount of data, but we still collect quite a lot, as I'll show you. So here's an occultation by an asteroid. So this is all set up. People knew where this asteroid was, and so we figured it was going to come within the field of view of Taos at a particular time, and they just trained the telescopes in that field, and they could see the occultation of the asteroid quite clearly, given by these 3 dips. Those are, I can't read the time scale, I forget it. Those are quite long by comparison to what you'd see if there was an occultation by a star. But it's sort of a proof of principle that the idea is not totally crazy. The data are recorded on a CCD array. Now you can think that the way a CCD array works is roughly the following. You have photons coming in from the sky, from this image, from this sky as you're looking up, and they land in the little buckets of pixels of the CCD array. And the way the CCD array is, the way you read data from the CCD array is you shift it to the last block of the CCD array, and then you read down that last block. Now, there's a problem with it. Just so you say, well, I can just open up the CCD array. Also, I should say that during the 90 minutes, the telescopes track the field of stars, so that ideally, over time, one star should illuminate the same set of pixels in the CCD array. That's tricky because you have to have the motors and the controllers and everything just going precisely enough as one can do that, and it's not completely realizable. But even if you could do that, there'd be a problem because the pixels in the CCD array would accumulate light from the background, and it would just run over the number of bits that are available in the CCD array. So what we'd have to do is close the camera, flush out the CCD array, open it up, read, close it, flush, open. But the shutter would quickly self-destruct under that kind of regime, so it's not really possible to do that. So we run in a mode called zipper mode, which is difficult to untangle, and I don't expect you to really get this, but I may just try to give you a quick idea. The idea is, suppose these are columns of the CCD array going along here. So we're in this configuration. The next time we shift the light, we shift the readings from the CCD array from one pixel down to another pixel, further down the column. And then we hold, we re-expose, and then we shift. So now this column has shifted, and when we shift, we read out. So you hold, you shift down, you hold, you shift down, you read out, you shift down, you hold, you read out. So you're just reading down this thing with these holds and shifts. So this is a little kind of this is an animation, so an idealization of how this works. So here they're shifting down. Now we hold, shift, hold, shift, and the bottom row is being read out all the time. So that's sort of what's going on. And here's a little segment of has some interesting feature. This is a segment of what you see in this last row block here. What you see during a succession of times. This is occurring we're sampling at a rate of about 200 milliseconds. So look at this. Let me do it again. I'm going to do it a couple of times. So you see the light from the stars should be landing like in the same place, like here, for example. Okay? But look what happens actually. Fix your eye on that spot. And you can see the thing moving around, right? Well, the source of that is largely atmospheric turbulence. It's as if the light is being shifted around, or the CCD array is being bent in kind of complicated ways. That makes it, and what you have to do is somehow you have to measure, whatever that means. You have to have a number which tells you what the flux was from that star during those 20 milliseconds. Of course, if you think about it, those 20 milliseconds here actually occurred earlier in time because it's been shifted down, but it's a complication we don't need to worry about. So that what's done is to put down you draw a little ring around a star, and you count the total flux in that ring. That's called aperture photometry. But you've got to move the aperture to track the star as this is going on, which is not easy. This is all done in software, of course. So here's the result. This is what we call a stereo image, what the sky looks like if you just take a photograph. And this is what the image does look like after it's been zipped. So notice the streaks going down. Well, those streaks, especially from bright stars, are caused by the shift, 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 hold, shift, 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 hold. So the shifts are pretty quick, maybe at, I forget, 10 milliseconds? No, something like that. But still, if the star is bright enough, it leaves these streaks. So this is the way the data from the occultation was recorded. Where did my stick go? We're running along through time here on telescopes A, B, and D. So notice there are 2 points here, there are 2 points here, and then one has disappeared. That's what those points are. That's the flux from a star. So that star there has now been occulted in those successive frames of the zipper image, and so what's done, this technique called aperture photometry is applied and produces these numbers, which are now the putative flux from that star over time. It's a very interesting process, this whole notion of how you do photometry. The astronomers have been doing it for a long time, but it's quite complicated, quite interesting from the standpoint of image processing. I wish I had gotten sort of my hand into this a bit earlier, but I really haven't been involved on the photometry side, even though a lot of the problems are very interesting and very statistical. Okay, so the thing is, so here we've got, at this time there are only two telescopes, A and B, because D wasn't working that night for some reason. And look, we see maybe that's an occultation, that dip right in the middle, right? Looks great. But now if we look at the zipper run, of corresponding to that time, what you see is the vertical strips which are caused by the lights from the stars. You also see the thing going across at an angle. So that was a satellite. So you have to worry about things like satellites. And of course, nobody knows where all the satellites are. You just can't keep track of them. So you just somehow the satellite streak's got to be recorded in the image. Has to be analyzed from the image. Here is like a massive spurious occultation. Now we have time going along this way. See this dark stripe there? It's basically clouds passing over the field of view of the telescope. These clouds can be very, very faint. I mean, you might not be able to see them if you looked up there. But these very high cirrus clouds can cause real complications in the data, and we'll see some more evidence of that later on. Well, some processing is done to try to get rid of big effects like this. So this is sort of the cleaned up zip array, but remnants still remain, as we'll see. Okay, so here's to give you an idea sort of roughly what we're going to be doing, what we do. So here's something that might be the occultation from a Kuiper belt object. So here are the light curves on A, B, and D, and there's this little dip that occurs simultaneously on A, B, and D. Now the hope is that no one would ever believe that that was real, right? You would just be thrown out within as quickly as the associate editor could read the paper, he'd reject it, because there's a lot of noise which is comparable. But if you have simultaneous dips on 3 telescopes, and if the noise is independent from telescope to telescope, then it's a lot more convincing that there's something going on here. So I'm not going to go into exactly how we do it, but essentially within one zipper run, with about 28,000 observations, on take one star, on A, you take those 28,000 observations, you rank them from rank 1 up to rank 28,000. You rank them on B and you rank them on D. And then you look for a coincidence of low ranks. And the test statistic we're using is just a product of the ranks. Well, you can just by sort of calculation, you can calculate what p-values are corresponding to that, or you can take the logarithm of the thing, which approximately follows a gamma distribution. But by whatever, so that event here, the probability of this occurring by chance, if the ranks are independent from telescope to telescope, and if at any one time you're equally likely to get ranks 1 to 28,000, turns out to be about 1.7 times 10 to the minus 7th. Okay? So that's pretty small by nominal values. As we think about p-values, that seems kind of small. But if you think about how many tests you're doing in a year, for example, and every year, every star in this field is being subjected to this same test every quarter of a second. So you're doing something like the order of 10 to the 11th tests like this each year. So if you're doing 10 to the 11th test, you shouldn't be surprised to see one which was just 10 to the minus 7th. So that, I don't know if people believe that's real or not, but even the most optimistic among the group might have believed for a while it was real, but in the end, you really can't say too much. Okay, let's look at some of the light curves. This is what comes out of the photometry. Okay, so I have 4 stars, and I've got the light curve. You can't. This is like 1 to 28,000 or something. Things are really compressed here. I'll zoom in a bit later, but here's a star on A, recorded on A, recorded on B, recorded on D. Another star recorded on A, B, and D. Now remember that our idealization is, though the flux from the star should be constant over time unless there's an occultation. But that's clearly not the case. There are all kinds of things going on here. I mean, it looks like if you look at A, for example, the trend here looks like the trend here, looks like the trend here, and those are different stars. Well, that can happen over 90 minutes. The background illumination of the sky changes. Clouds can go over for various reasons. There are other kind of weird things like this jumpiness going on here. We'll see that again later on. We see some big spikes in some of the data, some really substantial outliers. More funniness going on here. So let's look at a couple more. It's sort of endlessly entertaining. You just sit down and begin looking at it, and it's kind of a little frustrating too, because you've got 1,000 light curves to look at or 3,000 light curves to look at every 90 minutes. So it's actually still possible, I think, with this magnitude of data to go back and see what's actually going on, and to do a lot of visual exploration. But if you increase the amount of data by an order of magnitude, which is going to happen in coming surveys, then you're kind of in another realm. Okay, so here's some more. You see the same old trends again on telescope A. What happened here, this star I think was near the edge of the visual field, and the tracking wasn't perfect, so it kind of fell off the edge at the end of the run. There's something more going on, because they fall off the edge at the end of the run, but not in the middle. So there's maybe some sort of a cumulative effect of tracking error that causes this. There's this marvelous spike here, and here you see more spikes in the data. What are the sources of the spikes? Well, I haven't ever got a complete enumeration of all the things which can cause spikes. They can be caused by cosmic rays, for example. They can be caused because the software is driven by a clock on a Linux computer, and sometimes I'm saying things I don't understand. I'm told there are various schedules of interrupts which can throw the clock off, and when you throw the clock off, you may have integrated for a much longer time than you think you've integrated, and so you get a lot of flux. Here again is another tracking error down in here. Some more spikes and more trends. And again, this kind of funny business that we have in here of things somehow shifting in the middle. So now what do we want to do? Remember, this is not the kind of data that we want, right? Let me see if I can, just because, this point here has a small rank doesn't really tell us anything, because it's the trend which is dominating the rank. So we're supposed to have constant flux light curves. So you want to do something to correct the data. So what's done is in two stages. The first thing is you just take a window and you run, it works like this. You take a window of about 30 observations, and you run that window along, and you compute the median at the center of that window. So now every point is replaced by its median in that 30-point sliding average. And then you look at the difference between that point and the median. Okay, again, you have median runs along, and we look at the difference between the value you actually saw and the median in that window. So that's sort of like a high-pass filter, should flatten things out, and it does. These are the results. These are the same stars we saw before. Now the light curves are much flatter. I'll show you some more in a minute, but this is still not totally in a satisfactory state. We've got these, if this is all telescope A, for example, here, notice that the volatility is not constant through time. There's this period of time in which there's a lot of variation compared to other periods of time. And furthermore, making things worse, if you look at B, so here's A, here's the light curve on the star on A, here's the light curve of the star on B, and here's the light curve of the star on D. Now remember, we're looking for coincident low ranks. Well, probably you've got some in this region here, some simultaneous low ranks, but they're probably just due to the fact that there is more variability during that part of time. We'll see a couple more of these, if I can see any more. Well, yeah, you can even see, this is not so dramatic, but you can see it's sort of squeezed down in here, and it kind of has a lot of amplitude in there. So these are this sort of empirical problems. This is like step one of trying to fix things, but things still aren't fixed. And so what's done next is to scale locally by the MAD. So now you take you take a window, we take the previous results, we take our window, we rank the data we find the MAD of the data in the window, and we scale by that. So hopefully that should help, and it does. They're looking much more like the idealized curve should look. Of course, this is admittedly ad hoc, right? What is the window length? Why was that chosen? The other things we could have done, why didn't we do it other ways? Well, you have to do something, and this was what people decided to do. We still have the problem with spikes, of course, but you don't want to take out the spikes, especially you don't want to take out the downward spikes, because those are the things you care about. Here's more. The tracking errors are still there. So let's just look at a sequence then. This is one star. This is the original series from that star. This is a series after you've subtracted off a running median, and we still have extra volatility. This is a series after you scale by the MAD. And, things look great, right? I mean, but how do you know there's 28,000 points jammed in there?
How do you scale by the median absolute deviation?
Why do I?
How exactly do you scale by the MAD?
Okay, so we have the results of the previous thing, which is, so now we take a window surrounding the central point, and we find the MAD in that window, and then we scale that point, the deviations of that point by the MAD.
Right, in which case shouldn't all those
we take the MAD of the other
sequences
points. We take the MAD of the points around it.
Right, so shouldn't we expect those sequences to have roughly deviation 1? Shouldn't
Well, let's see.
do they actually? Maybe perhaps the scales are
So here, you can't see it, but this is like -4 to 4.
Oh, I see. Right.
You just can't see the numbers.
Right.
We're on original flux scales over here, which very dramatic. I should have pointed that out. Some stars are very faint.
Right.
Some stars are very bright. The faint stars have a much poorer signal-to-noise ratio than the bright stars do. And if you go back and you look at the data, you can kind of see that happening.
Okay. Sorry, I was confused by this.
So it's like ad hoc, robust smoothing.
Yes, but with trying to make the volatility constant. It's like an ad hoc robust smoothing, but then a subtraction. A smoothing is like a low-pass filter. You subtract, you make it into a high-pass filter. Then you scale by the MAD to make the deviations roughly homogeneous over time. Yeah, please do interrupt with questions as we go along. And after dinner speakers don't mind being interrupted. Okay, so here's just sort of amusing. Nate found this. So we just took 5,000 points. This is from one star. You take 5,000 points. Looks pretty. And this is after all this scaling has been done. So now we're running from about -2 to 2, which is kind of the range you'd expect to be in roughly about 5,000 points. Looks pretty good. But then what you do is you plot the data modulo versus time modulo 3.65872 seconds. So again, you change time to time modulo that number seconds. Okay, so it's called folding in astronomy. We're basically folding the data over and over and over and over again. And what emerges? This shape here. So there's some periodicity in this data, which you couldn't see so easily, but it's definitely there. Now, so where is this coming from? If you look at that number, we sort of stared at this number, 3.67582. You said, well, it takes 10 milliseconds to shift, 20 milliseconds to hold. By the time a star gets from the top of the CCD array to the bottom of the CCD array, one of those numbers like that, but no magic number came out. Furthermore, this number actually changes. So probably what this is, somebody have a guess? It's probably caused by shaking. These telescopes are sitting in enclosures up on the top of this mountain. Okay, there's wind. And the wind is buffeting the telescopes. And it's possible that there's a mode of vibration in the big enclosure, which, a fundamental mode with a period of maybe about 3.5 seconds, though nobody knows. That's the leading explanation. Now, it's kind of funny. This is another hobby of mine, periodic data. So look at the number, 3.65872. Now, let's fold versus a slightly different period. Now we're folding versus 3.658. Previous one was modulo 3.65872. This is modulo 3.658. So you have a Halloween mask. So you can actually determine these frequencies very accurately, and it might help. You might think it would help because we could take that out. After all, if that's there, if we could remove it, we'd improve the signal-to-noise ratio, right? So let me walk through these top columns, this picture here. This is the folded light curve. So here's the idea. Oh, we estimate the period is 3.65872 seconds. We fit with a sine and a cosine with that frequency. We look at the residuals, right? And so if you look at the residuals, they look like this. Not too great, not what you hope for, right? Well, then you can do what's called complex demodulation. For those of you who don't know what it is, it's like you do a local determination of the amplitude and frequency as you move along, centering on 3.652 cycles per second. And if you look at the amplitude, for example, look at the amplitude you get out of that little local window, the amplitude just drops. Okay, where does it drop? It drops there. So what's going on? The telescope is apparently not shaking during that period of time. So probably the wind died down. So it's not even a constant phenomenon, it's an intermittent phenomenon that's going on. The phase completely shifts corresponding. See, that alone is not going to work. Now, all this introduces correlations within telescopes. So here's a histogram of all the rank correlations within telescope A. So take telescope A, there's about 500 stars here. Look at all the rank correlations among those 500. Make a histogram of their values. Here's 0 here. You can't read this. Here's 0 here. Here's 0.05 here. Here's 0.10 here. So the correlations between stars tend to be positive. Same thing happens on B. The same thing happens on D. So that suggests that that there's a common signal which is there on all these different light curves, and if we could take that common signal out, we'd improve the signal-to-noise ratio. In the process of doing that, you would think that basically any phenomena on one star that was predictable by other stars would not be relevant to that star. So like for each star, you want to subtract out everything you could predict on the basis of all the other stars. You've got to be careful, of course, because you don't want to eliminate the phenomenon of interest in this procedure. So you might think the singular value decomposition would be useful. This would be like the first thing you think of, right? So I wish Ursula were here. Here are the eigenvalues. This is for one, I think this is telescope A. Here are the eigenvalues, a scree plot. It's got a nice elbow. Here's the first score function, which is a function of time. And that looks like that trend we saw, right? Remember those common trends we saw? So that's good because we could take that common trend out. We could basically think about if you have one star, compute the singular value decomposition of all the other stars, and then regress that star in the first few scores from the other stars, from that singular value decomposition. And that would maybe be good for removing the trend. That one doesn't look too bad. So that's a singular vector 1, 2, 3, 4, 5, 6, 7, 8. So this points out that the complete non-utility of the singular value decomposition if you have outliers or highly non-Gaussian data. Each singular vector is sort of devoted to finding one outlier. And then it takes on that one, then it goes on, then the next one finds the next biggest outlier. So the first one might have some information in it, but since you're basically doing least squares anyhow, I mean, you're just going to be in trouble. That was on the original data. Even you can do the same thing if you did the same thing on the filtered data, you'd have the same problems because you have spikes. So we had this simple method of robustifying the singular value decomposition, in which for every star we replaced this value at a time for that star by normal scores. Okay, so just put everything in terms of normal scores, then no more outliers. So it's some kind of like implicit copular model or something like that I'm using. I want to move on a little bit, so I'm going to go a bit quickly here. So these are the singular values. These are the singular vectors. Here's the plot of the first singular vector versus the time-wise mean, which is kind of what you would expect. It just picks up the mean over time from all the stars. You can look at the correlations of the stars with the singular values, and you find that this is magnitude down here. There's some interesting patterns that nobody has been able to explain what's going on. These are the brighter stars here. You think they'd be more correlated, but it's actually these stars in here which are more correlated with the singular vectors. You can do this to improve the signal-to-noise ratio. Here's star 15, the normal scores on star 15. Here's the corrected flux. So now you're going from a regime in which you're going from about minus, not a huge change here, but the amplitude here, yeah, the numbers are the same. You squeeze down things a little bit. There are little local corrections you can make. The dots represent the flux in that star. The line represents the predicted flux based on all the other stars. So you can take that out, which will improve the signal-to-noise ratio. Here's a case, star 115. The original series of flux or normal scores went like this. Notice going from about -4 to 4. We had this outliers, and then we correct it. It's interesting, this thing which looked like like an occultation or a dip was actually predictable on the basis of all the other stars. Now, and actually a more crucial thing for the validity of the test statistics is that the noise be independent between different stars. Because we use that idealization to multiply small numbers together and get really small numbers. So here's a picture of the ranks on telescope B plotted versus the ranks on telescope A. Okay? So for each point in time, we have a rank on telescope A and a rank on telescope B, and we're going to make a scatter plot of those. And apart from the discretization introduced by ranking, this should look like a uniform distribution on the square. How many people believe this is uniform on the square? How many people believe it's not uniform on the square? Clearly, you're not Bayesians. Okay, so it's really hard to see. I love this picture for classes because you can stare at this, and if you know what you're looking for, you might see something. But you know what your eyes do, how you find patterns and everything. If you smooth it a little bit, you find this. Okay, so it's high in the corners, the low ranks are correlated with low ranks, the high ranks with high ranks, and it dips down in the middle. Here's a histogram of the rank correlation between A and B, between A and D, between B and D. Here's 0 here. The rank correlation should be pretty close to Gaussian. And they look pretty good. You don't really see too much. Here it's kind of weird. There's some large negative rank correlation between A and D. Remember that A and D are the ones that are closest together. But if you compute the p-values corresponding to these ranks, and then you look at the empirical distribution of those p-values, which should be uniform, here's what you get. Here's uniform. Here are the empirical distributions. So they're small, very small, like correlation is 0.02 or 0.003, but they're there, at least in this particular series on this particular night. You can see it also if you look at the singular values of the cross-covariance matrices of the data subjected to normal scores and etc. Those cross-covariance matrices are not 0. How are we doing? Okay, I think we make it okay. Here's some more signs of dependence. This takes a little bit of explanation. So now at each time I've got a a value for each star. So say there are 500 stars. So at each time, I take those 500 values and I compute their median. Okay? So this is a sequence of the medians of all the stars on telescope A through time. Okay, so what's interesting is this scatter. In this region here, those medians are oscillating a lot more than they do at other points of time. They're becoming more dispersed. And you see the same thing happening at around the same time on telescope B and telescope D. Now this is probably due to either wind or maybe people seem to favor like high cirrus clouds. Cirrus clouds actually have very high frequencies. I mean, the way they let through light can be quite high frequency. So there's more of a sign of dependence. This is bizarre. Did the same thing, but find the MAD. Take all your readings at time 1 on telescope A, find the MAD. Take all the readings at time 2, find the MAD across stars. Okay? And then plot that sequence of MADs, which looks pretty good, but then you get here, like what is going on? The MAD has dropped. All of a sudden, there's much less variability among those medians than there was before. And there are other little periods of time in which the same thing's happening. And then this is undoubtedly caused by those dropouts, right? The tracking errors at the end. One more picture in this series. Again, for A, taking the same data, that each time you've got 500 observations. Plot the median, which you've seen, and the upper 90th percentile and the 10th percentile of the data through time. So now you can see when the median begins to shift down, well, the other percentiles tend to come down also. It happens at the same time on all the stars. Here's the situation in which, here you can see that the 10th and 90th percentiles are actually shifting in. And that was that period of time in which the MAD dropped. And here's the bit at the end. The lowest percentiles get really small because of a dropout at the end of the observation time. Okay, I want to say something about other goals of TALIS. So we've seen this median MAD filter is not perfect, but it's not crazy either. Some corrections can be made. So so it's like good enough for government work, basically. But there are other times in which that high-pass filtering is not appropriate for other aims of TALIS. One of the things that TALIS would like to do, sort of like a little spin-off, is to detect extrasolar planets. So imagine you're monitoring the light from the star, and there's a planet that's circling the star, and it happens to intersect. It's oriented correctly so that it will actually occult the star as it passes across the face of the star. You should be able to see that as a slow dip and then a rise in the light curve from that star. But that takes quite a long time. I don't have the time scale here, but this is a transit that was recorded on TALIS A. And these are several minutes at least that this thing took, maybe an hour. I don't want to do the arithmetic in my head. It'd be embarrassing to say 1,000 bins per point. Each number should be multiplied by 10 to the 4. Take this number, subtract that number, multiply by 10 to the minus 4, figure out how 1,000 bins comes in. But anyhow, it's a pretty long period of time. And anyhow, so that would be killed by high-pass filtering, right? It would just wipe it out. So you do need to adjust the data somehow. And you need basically to detrend each star based on the behavior of all the other stars. You need to subtract out the conditional expectation, the flux from that star given the other stars, however you compute that conditional expectation. I want to show you a little bit of some data I just got last week. I was in Boston for a TALIS group meeting. There's a woman named Federico Bianco who was taking data looking for occultations on another telescope, a huge telescope, a 3-meter telescope, telescope in Arizona called the Multi-Mirror Telescope. Actually has many mirrors, and the data are recorded on a mosaic of 72 CCD arrays. And it's operated at 200 hertz, so it's really fast. So she should be able to see all kinds of things. If she sees an occultation, the atmosphere is good as up in Arizona. The duration of the thing is long enough that she should even be able to see certain kinds of diffraction patterns, which would be, which you should see if you really monitor the things exactly. So I was talking to Federica, and we got some of her data, and here's the data. She had like 264 stars sampled at 200 hertz for about 10 minutes. There are about 60,000 observations in each of these time series. And these are I just barely began to look at the data, but it's so interesting. So this is just the first 10,000 points out of 60,000 on one star, on another star, another star, another star. Okay, now this again should look like white noise unless there's an occultation, but it sure doesn't. There's even a drift in this one. Of course, if you look at the numbers, this is the faintest of these stars by far. So that may account for what's going on. But look at these oscillations you see here. And you can kind of say, well, look, this one sort of looks like that one, right? So maybe we could detrend. Okay, Federica really wants to detrend these data.
So are these round?
No, this is just flux. Just flux. Nothing's been done to it. But the data is cleaner than the Taos data is. There are fewer atmospheric effects, but except for this kind of oscillation that's going on here. So what do we see? Well, here's a 3x3 plot of the autocorrelation and cross-correlation functions for the first of those three stars. So this is the autocorrelation function for star 1, for star 2, and star 3. Remember, star 2 had that trend in it, and that's why, of course, the autocorrelation function is dropping off slowly. And you see these very distinct ripples in the autocorrelation function, which are consistent with this, they're consistent with, with this oscillatory behavior that you see. And then we have cross-correlation functions. So this is, let's look at this one here. I can remember how to read. This is lag 0 to 200, and this is lag 0 to minus 200. It involves stars 2 and 3. And you always have to go through this horror of arithmetic, and at least you keep notes about which one's in front of which one, and et cetera. But what's kind of interesting here is the cross-correlation functions also ripple, right? Not surprising, but look, at 0, they're small. The cross-correlation function is maximized at some kind of a lag. So one of these stars is actually leading one of the other stars. So a quick comment, what's going on here? Well, it's the wind again. No one had ever recorded data at this kind of data rate on the multi-mirror telescope. It's usually used for much longer exposures for which this kind of phenomenon would never be seen. So here we've got, here are 3 power spectra. So these are the 3 power spectra for these three of these 264 stars. There's a very predominant spike. I can't what the frequency is. This is cycles per second. About, what, I don't know, 2 cycles per second or something like that maybe. And there's similarity between this one and this one. Begin looking at the details. This one's a little bit different. There's still that frequency, but these other frequencies aren't there. Or maybe they are, but they're a much reduced scale. Of course, it's a bit hidden because this has more low frequency behavior, so it's boosted up here. I don't think I made a plot, but you can begin looking at things like coherence. So you would think this should be not too bad because, well, we can just somehow do some sort of massive cross spectral analysis. But again, the problem is it's like you think of a telescope as being like a bell. You have a bell here, and I hit it with a hammer, get a big gust of wind, and the bell rings, and then it dies down, okay? Get another gust of wind, it rings again at the same frequencies, but now they're out of phase with the frequencies earlier on, and there was that period of time in which there wasn't any, in which the amplitudes dropped. I mean, it's quite suggestive. I mean, it's quite, I'm sure that many of you have some good ideas, even just probably some of the very first things that occur to you be reasonable to try on the data. Yeah.
Well, there's the data analytic point of view, but aren't there ways, instrumental ways, mechanical ways where they can, you can sense the wind and try to...
Well, actually, they went back and they worked on, they were so surprised by this at MMT that they went back and they tried to improve some of the feedbackness in the motor mounts or something. Now, I don't know if that's been successful or not, but it's pretty expensive to redo something like that. Yeah.
Do they even measure the wind?
Well, I don't know if you can measure on that time scale. I don't know. You would think we could measure the wind. It would be like a nice covariate. The other covariates too, so it gets more complicated because the data, say, is recorded on a mosaic of 72 CCD arrays. And so one CCD array might have 10 stars, another one 8, and then 6, 14, and etc. And in this mosaic, in the top half of the mosaic, the data is read this way, and the bottom half this way. Now just imagine you're just looking, so what happens here, one of the things which happens is that you read the flux in that pixel, okay? But if that pixel is moving this way while you're reading, you're going to get more flux. If it's moving this way, you're going to get less flux because less time has actually elapsed. But then there's motion in the other direction too. Anyhow, so I think it's just a fascinating set of data. I don't know what we'll do exactly, but it certainly will be fun trying to look at it. So all this hard work by astronomers, and these are astronomers carrying this Taos something B up on the top of Lulin. There are so many interesting statistical problems in this and other astronomical data too. The data are not publicly available yet, but we're setting up a website, and our intention is to make the data completely public as fast as we feasibly can. But that entails getting a website set up which works, we've got the bugs out of it. We have to put some documentation up so people have some idea what they're getting off the website. So it's not available now, but the intention is to get it, to make it publicly available by 2009. Then you can just go and you can download all these light curves. Final remarks. Okay, so some reflections on the conference and on this data set. These data sets are challenging. Hundreds or thousands of time series, which are tens of thousands of points long, which somehow should be simultaneously analyzed. And you can kind of do it. Also here, we're actually aided by the fact we're looking for these occultations, which are very rare. So if we think we see one, we'll go back and look at the CCD array image at that time, and that data will be subjected to really heavy scrutiny, which we can afford to do. But if we're recording dozens of events per night, it'll just be overwhelming. So some surveys and projected surveys will produce much larger sets of data. Now, I think one thing that happens, you see it here, and it seems prevalent, that when you have massive data, you don't get more independent copies of what you had before. You get copies which are more heterogeneous. There are different star fields, there are different observing conditions, there are different telescopes, different nights. So there's sort of an allure, and it probably isn't a totally false allure, of trying to think about some kinds of things like hierarchical models to incorporate this heterogeneity. Sort of a natural move, at least by the way we're trained anyhow. There's also some burden at the end in a project which is trying to detect things that people can understand what it was you actually did. That is, some need in order, if you're going to publish in an astronomy journal, the readers have got to be able to understand what you did and believe it, and understand it clearly enough so that they're convinced that it makes sense. So that, in some sense, that limits maybe some of the things one might do. A lot of the themes of this meeting are relevant. I think you can see them, things like ideas of problems of multiplicity, which Tony Kai was talking about. Ideas of model selection, dimension reduction is clearly important. We saw the need for robustness. You could think about using something like independent components analysis on some of this data. You have to be a bit careful. You like data to be non-Gaussian for ICA, but probably not this non-Gaussian. You could think about using graphical models to adjust all the light curves together. But I wonder, so these are the ideas which come to my mind, if I think about this. But to what degree, am I seeing my own reflection when I look in this water? That is the reflection of the ideas that I know about and the training I've had and what I hear from my colleagues. Lots of good ideas. But I think that, the Bible says, not that I read it all that much, but it says, for now we see through a glass darkly. And I think we do, and I think that maybe there's a little more light because of conferences like this and the efforts of Mike, Peter, and all the other people who've made it happen. So one final thank you to all of them.
Second thank you to John. Anyway, we'll have our chance. So, questions? Ideas?
Jane?
Yeah, so there are 500 stars there.
Yeah, say.
Each one produced a curve.
28,000 points in the curve.
Yeah, okay. But you said earlier, I guess, you believe they should be constant, except for some ditch.
Yeah.
So if that is the case, why not combine and then say, assuming each one has a constant which varies from one to the other?
Yes.
So it's like you have a random, constant curve across it.
Mm-hmm.
And then you subtract that off and do some kind of either principal component or whatever. Because if there's any wind or cloud or whatever, you would expect it to
subtract the local the average time point
now
by
you estimate, you assume each one is a constant over time.
So I
a
fit-
random constant,
Uh-huh.
right? Because that's what you believe the general
So then I
trend.
collect deviations from that constant, right? Then I measure the deviations from that constant.
Yeah, let's see. Yeah, but across all the stars, right?
Yeah.
Because you want to recover what causes, what are the major trends
Right.
that is involved in all the 500 stars. So wouldn't you be able to discover that through the secondary analysis? I mean, either ICA or principal or in.
Perhaps. I think I sort of see what you're saying, but I don't think I see it precise enough, or even if I do understand it, I don't understand the consequences exactly. But but I think that the basic idea is right, that somehow you want to use information that's in all the stars to correct an individual one. So if they're all up, you want to take account of that and bringing them all down, right?
Yeah.
I'd like to sort of go at the second last line. Is this a large enough collaboration that there are several groups of data analysts, and can you sort of look at between group approach?
No, it's not. There's me.
So,
It's not as that the astronomers do a lot of data analysis, but yeah. That's one thing I'd like to be really kind of neat. We can get this up on the web, and then people can take it, use it in classes, see what people do with it. Yeah, the between statistician variation we haven't taken out yet.
Other questions? Well, maybe if I might just ask a small one.
Yeah.
Is there any consequence of stars being seen in adjacent CCDs or something, sort of
Yeah.
local effects?
Yeah, I think that even going back to Taos, which is simpler as one CCD, the stars actually have locations on that CCD array. And that presumably, those locations are relevant. So stars, with the CCD array is actually, it's as if they even bend. They don't really bend, but the effects of the turbulence are such that the CCD. It's as if the CCD's rays were shearing. So you might be able to take stars which are nearby and do something with them special, or at least you might like to see, to use that somehow as some explanatory, as a covariate. Yeah. I've really made a couple of plots that look like their effects, but we've really done very, very little along those lines.
More questions? Well, if not, let's thank John for a wonderful talk.